Is the screen visible to you?
Yes, sir.
Okay. Okay. Let's start then. So today we are going to next chapter, that is impulse and momentum. Impulse and momentum. Okay. So for doing this, let's go back what you have learned, that force F equal to ma. 10 plus 2 standard also you have learned this. Now here F become summation F, basically resultant force equal to, maybe vector form, it is ma. Component form, summation fx equal to max, summation fy equal to may, summation fz equal to maz, component wise. Okay. Now with this, we'll add this, that when summation f equal to ma, this a acceleration basically m dv dt. Okay. When m is constant, we can write this as d of dt of mv. This is summation f. That means, and what is this? This is linear momentum.
Momentum.
Yeah, linear momentum. Okay, not angular. Linear momentum. So if we denote this by g, linear momentum, then basically summation fx equal to this g. If I write linear momentum also vector form, g dot, that means rate or time rate of change in momentum equal to resultant force. Rate of change in, let's write linear momentum. Linear momentum is the summation of f, resultant force. So linear momentum we got here, g equal to mv of the particle. Here how we can show, say this is the path of the particle. Now at time t1, position vector r1, time t, position vector r, time t2, position vector r2, and that path tangent is velocity here v1, it is v, it is v2, and this v is nothing but r dot, derivative of position vector. Okay, now maybe we have applied summation f x like this, and resultant force is acting along these directions. So we have x axis, y axis, and z axis. 3D case we are resolving. Now what we can get, that summation f, along that action, okay, we call line of action, there will be accelerations a, that is nothing but v dot. So in the directions, the same line of actions will have acceleration or v dot, and whatever the directions this v dot will act, this rate of change of momentum also will act in the same directions. That's why we says this 3/25 expressions, that the resultant of all forces acting on a particle equals to the time rate of change of linear momentum, and it is linear momentum unit is, if somebody can go, summation f, correct? Summation f was force, that was Newton with respect to time, Newton per second. It is Newton per this is Newton d of dt, correct? Force. This one force is Newton, sorry, this was Newton and this was Newton second per second, right side. Okay, so the Newton second was the MB. No, MB unit, what was the unit of MB then? Somebody can write this way. This is MA accelerations. So, or we can write directly in previous one here. From there we can write Newton equal to MB. Say somebody can write directly kg meter per second. Kg meter per second, or if you want to convert this, it is kg meter per second square multiplied by second, then it is Newton second. As this is Newton second, divided by time will be same unit of Newton. Now it says that when we are talking about say summation f or g dot, they are equal. Component wise, if we want to write this, summation fx will be this, fy will be this, and fz will be this. Now, if we have this force summation f and we have multiplied with ds to get the work done with respect to distance, we have done the integrations. Now, if you do this similar way, summation f dt, then we will get impulse, linear impulse. Okay, I should write linear impulse. Now, if I write this way, summation f dt, what we have learned before, that summation f was d of dt of g. Okay, here it is multiplied by dt, then this is dg. Just change in momentum. That means if you do the integration like this, t1 to t2, then it is integration t1 to t2 summation f dt equal to, this is nothing but g2 minus g1, what? Delta g. So this impulse equal to change in linear momentum. Linear impulse equal to change in linear momentum. So this is impulse this is the momentum. So I can write linear impulse, this is linear momentum. That indicates that if we have two cases, say this linear momentum initially was mv1, it moves to mv2, then this mv2 minus mv1, this change in linear momentum equal to summation f dt integrations, say t1 to t2. So total impulse on the particle m, particle of mass m, equals the corresponding change is linear momentum of m, or mathematically we can write g1 linear momentum at step 1 plus this added, this is say added impulse, will be final g2. If this has been added to the system, then this g2 will be higher than g1. But if it is not added, it is doing some reverse directions, or maybe it is not positive value, negative value, then g2 will be lower than the g1. We are just exercising 10 plus 2 standard concept here. Now when we are writing, we want to write component wise, then in x directions, mv1x integration t1 to t2 fx summation fx dt m v2x, y directions and z directions. We can get these three component wise linear impulse momentum equations, and these three components are completely independent. Now we want to write the similar way. We have drawn free body diagram. Just a minute. Just wait, okay? Just wait. Okay. Sorry, just a minute. Okay. So what we told, are you able to hear me now? Hello?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
In free body diagram, we have dealt with force. Okay. Now here we can have similar way impulse momentum diagram. So it is not free body diagram, it is impulse momentum diagram. We can construct this diagram also. How? So we will utilize this expression or previous page these expressions. So what we'll write here, say particle 1, we have only one particle. Initially it is m v1 is the initial momentum, both magnitude and direction wise, this one. Plus we will add this impulse. This is momentum number 1 initially. Then we have added impulse. So this dt, and this is a summation f. Summation f direction is the these directions, and it is integration over t1 to t2. Time is dt. So time span is dt. Okay. Now if I add this, so unit wise, as I told, it is Newton second, isn't it? This Newton second plus this Newton second. If I, is this also Newton second, f Newton and t second. So Newton second, it is also Newton second. Vectorically we are adding. So this and this. So final will be this. So this is the momentum 2. You have to be careful. It is not for a free body diagram. It is impulse momentum diagram. Similar way we can draw. Okay. Similar way we can draw that one. So this plus this equal to this. That means when you are calculating this, you have to be careful not only for magnitude plus direction also when we want to solve this problem. Say in 1D cases, everything is along these directions, no issue. In 2D cases, as I told, we can utilize this expression independently. We'll utilize this. But vectorically, if somebody want to show this, then instead of free body diagram, you supposed to get impulse momentum diagram, and that has been shown here. Now, one thing you have to be very careful that when we are drawing this type of diagram, this impulse, okay, impulse will be associated with, okay, so when you have applied some force on the systems, so like some external force, you have applied the force on the systems. Now based on the what time you have it is been involved, external force you have applied, you can calculate as per this 3 bytes 27 or 27a and b, these expressions. Now there are many other cases when you have you have this this momentum change due to say two bodies 1 and 2 for very short period of time, say 10 to the power minus 6 seconds. So we are talking about impact. So in that case there will be some force associated with impact force, okay, it will be associated with impact force, and we are assuming that that impact force is much higher than the other forces. What are the other forces? Let me tell you. Say here it's these expressions. So when there are two bodies collide, there will be some impact. So there will be some forces, compressive force. It will give one to another one. Say it is say plus F, this is a minus F, same magnitude, opposite directions. But if it is having it is having some maybe I'll show you this way, these vertical directions, these directions and these directions, okay, these directions, maybe this is the collisions we are talking about. Then it is having some its cell point, say M1G, it is having some cell point M2G, or maybe W1, this is W2. Then this W1 multiplied by dt will be another impulse. Here W2 multiplied by dt also another impulse, but we can neglect this impact sometimes when this force exerted due to the impact between two bodies, that value is very high compared to the weight of the two bodies. So we can neglect this impulse due to their cell point, and we can utilize this expression like mv1 plus summation f dt equal to mv2. That expression we can do. Just a minute, another call. Wait, just a minute. Okay, just a minute. Okay, so in that case the cell point impulse due to cell point will be discarded. Now same thing, it has been told that in certain case force are very large, this is very large, and in a short duration of time, such as that, such force is called impulsive force. So it is impulsive force. Other forces are non-impulsive force. Okay. Say for examples, for that is when there is any sharp impact, we are assuming this impulsive force is constant over the time, and we can brought it outside of the linear impulse integrations. And frequently we assume that non-impulsive forces can be neglected because their values are very less compared with the impulsive force. Say for example, the non-impulsive force of the weight of a baseball during say collision with a bat, some racket and ball, 5 ounce. That weight of the bat, sorry, weight of the ball is much higher than the force exerted due to the impact of the ball. Due to the impact on the ball by the bat, say racket and tennis bat when we are talking about. Now what we understood that when we have initially impulse plus initially momentum plus you can add this impact to get the final value of the momentum. Say for example, as I told, this is one impact due to the racket bat on the tennis ball, and we can assume that this impulse due to the cell point of the racket ball that is much lower than the force exerted by the exerted on the ball by the racket bat. Now, in case, but what I told, in generally we can assume that these contact forces are very constant, and it can come out from the integration. We can simply have F multiplied by dt or time span t2 minus t1 to get the impulse. But when force is not constant, it is varying with time. Say this is the different. This is the graph of force versus time. Force versus time. Okay. Now, I am interested to check that impulsive force between T1 and T2, two time step T1 and T2. Then we can have this area under the curve, and this area under the curve says this is Newton, say this is second. So this unit will be Newton second. That is the representation of impulse. That is the representation of the impulse, and that value added to the system will be the same value, will be the change of the momentum, linear momentum along that particular directions. Okay, that's all. Now, say for examples, we are not applying anything externally. So summation F, that is 0, no external force has been applied on a particles. Then we can consider that linear momentum G will remain constant. That means that linear momentum will be conserved. Linear momentum will be conserved. So, say for example, there are two bodies, they are colliding to each other, and the forces exerted, say this is F plus F and this is a minus F. Between this, no external force applied. Then we can consider that as this is the F and this is a minus F. So F dt, one case it is F dt, summation F dt, another one is minus F dt, that is the two impulse. Okay, this is the two impulse we are talking about, and they will be nullified. The thing we are doing anything. So in that case, it can be considered that in one case momentum will change in the momentum. G stands for momentum, is not it? So change in the momentum will be 0. That means initially, if it is say 1, particle 1, particle 2, then G of A plus G of B will be same as G. Okay, same as G. It will be no change. If I consider for the only one particle, the G1 will be G2. If it is one particle, it will be G1 equal to G2. So, and that is the expression for principle of conservation of linear momentum. So what basically we are doing, whatever relationship we are having here, this plus this, if this impulse is 0, then this will remain same here. So conservation of the linear momentum here, that will be valid. Now let's have these examples. There is one tennis player who strikes the tennis ball. Here, this is a tennis ball with a racket when the ball is at the uppermost point of its trajectory as shown. So this ball is moving like this, and this position is the uppermost point. Then uppermost point. Okay. Then there the man hits, and if it is the horizontal velocity of the ball just before the impact with the racket is horizontal velocity, say v1x is 50 foot per second, and just after the impact it is v2 basically, because here there is some angle here, v2 equal to 70 feet per second, and detected with the angle alpha equal to 15 degree as shown. The 2 ounce ball is in connect with the racket for delta t equal to 0.02 second. Determine the magnitude of the average force F exerted by the racket on the ball. Also determine the angle beta, which will be made by this resultant R with the horizontal. Okay, with the horizontal. So let's have impulse momentum diagram. So initially V1, it is horizontal, mv1 initially, plus some impulse. Then this momentum, first momentum is, second momentum is, this is the x-axis, this is the y-axis, it is mv2, it is making angle 15 degree. Okay, 15 degree. Now you can check here, we are not considering anything regarding its self weight mg, that has been neglected. Okay, mg multiplied by delta t, that has been that impulse has the impulsive force has been neglected. Okay, so now we could have x and y directions. So we can have this rx in x directions, ry in y directions. Okay, rx and rx and ry here, very you can notice that this rx multiplied by dt is the horizontal directions. It is been shown here. Let me change the color. Okay, in color, let it be this. So this one, then two direction is this, r2y dt. You be careful here, mg has been considered, mg dt, this has been considered here. Why, I will tell you. Then multiplied by dt and t1 to t2. This is the scenario. Now if somebody is working for say x directions, you concentrate on x directions in x directions. So mvx1 plus t1 to t2 fx summation fx dt plus mvx2 in x directions. In x directions it has been conserved. Now what is m? Actually 1 ounce oz equal to 1 by 12 pound. That's why it is 2 by 6, sorry, 1 by 16 pound. 2 by 16 multiplied by g. G is 72.2 foot per second square FPS unit. So that is m, because this ounce or pound we are considering, instead of force we are considering, let it be weight. We are not going to this to poundal, let it be weight. Pound is weight. In terms of pound we want to show the results. Reaction force also in terms of pound. So this is the mass we have written here, multiplied by what? Velocity. Okay, what is the initial velocity in the horizontal directions? What is the initial velocity in the horizontal directions? The horizontal,
sir, 50, sir, 50.
It is 50. Okay, horizontal direction it is 50. So okay, we are here, this and this. Okay. Now as this is directed these directions, these directions, so we have minus sign. So minus 50, you are right. Plus positive directions, rx, as I told, we may consider, we can assume that this impulsive force is constant over that short period of time, delta t equal to 0.2 seconds. So rx multiplied by 0.2, it is second, and this is pound. Be careful, this is pound, this is second. That's why it is ounce. We have converted to pound, but at it is this 1 by 16, but still we have divided by this to make sure force is in pound. I will tell you once again. So it was mv, okay, and it was rxt. We want this pound second. Now this velocity, definitely this will be foot per second. Now mass we want. Have I missed anything? Okay, yes, Now it is mass. If I use mass equal to pound, then pound, this is F, correct? Rx, yes. So F, this pound multiplied by this will not be unit of this. So what we did to get this equal to this unit, pound second. So what we did, we have divided this foot per second square. Then this will be cancelled out, this and this will be second. So it will be pound second. That's why it was how much? Let me check. 2 ounce, I guess. Let me, yeah, 2 ounce, 2 ounce, 2 by 16 pound divided by 32.2 foot per second square multiplied by foot per second. If it is so, then this will be cancelled out, this will be cancelled out. Whatever value will get, it will be pound second, because this is Rx we want in terms of pound. Okay, so we got left side, then right side is similar way, m multiplied by velocity along the horizontal directions. So it is told that V2 for 15 degree angle with the horizontal, so V2 cosine 15 degree. V2 is equal to 70 meter per second. Sorry, foot per second. So this is done. In this problem, only unknown is Rx. This you can calculate 22.8 pound. Now Ry. For Ry directions, see MVy1 plus impulse in y directions equal to final MVy2. Now initially velocity of initially in y directions Vy1 was 0, because velocity it is told it is only horizontal velocity. Okay, then only horizontal velocity, there is no vertical velocity, because when the racket hits the ball, it is told that a tennis player strikes the tennis ball with her racket when the ball is at the uppermost point of the trajectory. From this to this uppermost point, that means Vy was 0 here before impact. Vy1 was 0 and Vx1 was given as 15 feet per second. So initially we have velocity is 0, then Ry delta t minus its mg, okay, multiplied by t. But as I told, we want in terms of pound only. So mg we are not multiplying with g. So 2 by 16 divided by time. You have to be careful. This one we are considering. Why, I will tell you. So then we will get equal to final velocity, and Ry will be 3.64 pound. Here you have to be careful that we note that impact force is 3.64 pound, is considerably larger than the 2 by 16, that is 0.125 weight of the ball. Thus weight mg can be considered as the non-impulsive force and could have been neglected as compared with Ry. Had we neglected weight, we can compute the value of Ry is 3.52 pound. Here 3.64 pound. This is when mg you have considered, when you have not considered mg. That means due to this impulsive force, that is 22, Rx was 22.8 pound, Ry was 33.64 pound, that is much higher than considerably larger than the weight of the ball, that is 0.125 divided by 3.64. Let me check the ratio, because what is this? It will be only subtraction of between these two, correct? And that will be multiplied with time. Actually, this impulsive force will be subtracted. So let me check how much value this is compared with Ry. It is 0.125 divided by 3 point, I'm calculating 64 multiplied by 100 percentage wise. So it is only 3.4 percentage. And when we are neglecting these terms, we are neglecting this term as a 0, we are considering, then we are getting 3.52. What is the error? Percentage of error now? 3.64 minus 3.52 divided by 3.64 multiplied by 100. Error is error due to not considering that one. That value is, just a minute. Let me check. 3.29 percentage. Okay. Anything if it is less than 5%, we can neglect. It's thumb rule. Okay. But obviously, if you can consider, you will be getting the more accurate results. Is it any issue for this problem? We can repeat. If we have any doubt, we can repeat this problem. Is it okay? Anyone has to respond, yes or no?
Yes, sir. It's okay.
Okay, fine. Next question is, we have a loaded 150 kg skip. This one. 150. Okay. Wait. If this is 150 kg. Let me change the color, ink color. Okay. 150 kg, and that is rolling down. So rolling down, that means this is the accelerations with the velocity 4 meter per second. When P force is applied to the cable as shown in the figure. So I should write this way: T equal to 0, V equal to 4 meter per second. That is the better way to write. Okay. The force P has been increased uniformly with the time until it reaches 60 Newton at T equal to 4 seconds. So initially it was 0, then up to 6, this T equal to 4 seconds, P Newton was 60. It is monotonically, uniformly has been increased until it has reached at 60 Newton. After which it remains constant at its own value, at this value. Calculate the time t prime at which the skip reverses its directions, and B, the velocity B of the skip at T equal to 8 seconds. Treat skip as a particle. Okay. So this one we will consider as a particle. Initially velocity is given here. Okay. Now, if we want to draw the impulse momentum diagram, let's consider initially it was M is 150 kg, V1 was 4 meter per second. So initial momentum was M1 V1, 150 multiplied by 40 kg meter per second, and this angle is 30. So this is been shown initially, plus as the force has been applied, there will be some impulse. Let's draw that impulse momentum diagram. So in this case, here there will be one reactions. This will be another reactions. And if it is N1, it is N2. Then this N1 multiplied by dt. This will be N2 multiplied by dt. And its self weight is along this mg, m multiplied by g multiplied by dt. And here, if this is p, you can check it. If it is p, if you cut here, if you cut here, then it will be p, this also will be p, is not it? And if it has been p, if this is p, to make it tension, it will be also p. Now, if this is that free body diagram, sorry, that your isolated regions, then p plus p will be acting, 2p. So this 2p is acting over there, multiplied by dt. Why 2p? Because you have applied the p using the string, using the cable, but here it is experiencing p plus p, 2p forces. So it is 2p. So what we have drawn, impulse momentum diagram. It is not free body diagram. Instead of free body where force are being involved, here impulse and momentum are involved. So it is impulse momentum diagram. And it says initially m1 v1 plus impulsive forces and self weight also equal to final one. What is the final one? It is told that finally it will have some velocity we don't know till now. That was 150 multiplied by v2. See, we are considering forces. What we are considering, either impulse or momentum. So this is the impulse momentum diagram. What is this? Impulse momentum diagram. Now, part A, calculate the time t prime at which the skip reverses its directions. So it is initially moving down, then it will start to move up after some time. So when it will start taking reverse directions, velocity will be 0. We will assume that these conditions t prime is 4 plus delta f. An impulse momentum diagram is applied in the x direction. Which is x? We will consider this here, it is x and this is y. With the inclination, it is x. I told x does not mean it is horizontal, it may be inclined. So even people are writing summation fx equal to 0 without showing x and y directions. Okay, I have deducted marks, you have seen. No? So you have to be careful, you have to show x and y directions with this coordinate x and y. Here it is, this is x and this is y. So first of all, in a positive x directions. What is positive? This is the positive x directions. So it is in positive direction m v 1x plus fx dx, sorry, fx dt plus m v 2x. So 15 minus 4, because it is negative directions, 4 meter per second. Okay, and what is the final destinations? 150 multiplied by 0. Now, what is fx, summation fx dt? Very careful, f is not constant, f has been varied. This f has been varied as per the given curve. Area of the curve will give area of ft curve will give the impulsive force. So what is this value? This one, half multiplied by 4 multiplied by 2 multiplied by 600. Why? Let me check. Half multiplied by 4 multiplied by 600. multiplied by 2. Okay, why? Why this 2 has come? I understood this is 0 to 4 multiplied by 60. Then why this 2? Can you tell me why this 2? Once again, if I go here for this area, it should be (60) multiplied by delta t. But why this 2? Why this 2? My question is why this 2? Then once again you can see. Can you tell me why it is 2? From where 2 has come?
Sir, P plus
I
P is
think
2P.
it's from 2P.
2p, very good. From 2p, yes, from 2p. So that is good. Then minus. So we are here basically in x direction along x. So this 2p dt is over. So we have calculated this one from here. Minus which one? Minus this 150 multiplied by mg multiplied by 9.81 dt. If it is, this will be theta. So it will be cosine sine theta. Yes, sine theta. This cell w sine theta multiplied by 4 plus dt, because total 4 plus dt, it is 150. Then delta t equal to 2.46. So this one 2.46 second. Total 4 plus 2.46, 6.46 seconds. So what is happening? Initially it is fine. When you are monotonously, continuously increasing P, it is slowly it is moving down. But once you stop with a constant force of 60 Newton, then after some time it has reversed the directions. So velocity was 0. Now it has asked what will be the velocity of the skip at the t equal to 8 second. Okay, when t equal to 8 second, when t equal to 8 second, what will be the velocity? Okay, so what I'll do, let's say from the beginning itself, t equal to 8. So applying the x directions, similar way, this m v1x plus f dt plus equal to mb to x. Maybe here we can consider this is 150, let it be, this is the unknown. Time you consider same, don't skip, don't go from 6.46 to this, you start from the beginning, no issue. So this is the mb, then this is the total up to 8 total area, then minus mg sine 30 degree, then t, you will get this velocity. That means it is indicating that it has started with 4 meter per second. When when velocity started from 4 meter per second at t equal to 0, then slowly somebody has applied the force P from 0 to 600, then it remains constant, and at t equal to 6.46 second, it stops and starts reverse direction velocity, and at 8 second means in 8 second means here, in 8 seconds means here, it is having some reverse direction velocity, and that velocity was 4.76 meter per second. Have you understood? Any doubt up to this?
Sir, can you repeat the last part?
Yes. So initially you did, and we got delta t was 2.46 second. Now then t prime will be 4 plus 2.46 equal to 6.46. Okay, so we got here, this is 6.46. Now it is told, now try what will be the velocity of the skip at t equal to 8 second. Okay, t equal to 8 second. Now what we are doing, we have initial conditions v equal to 4 meter per second downwards, and if I consider total t 8 second, then this graph up to 8 second will give what will be the impulsive force applied, and that impulsive force is this. Sorry, the total impulse is this. If I utilize this expression once again, understood? When we are applying this expression once again, where V2 is the unknown, and starting from t equal to 0 itself, then you can get this velocity V2x equal to 4.76 meter per second. Am I clear?
Yes, sir.
Actually, trick is initially it was downward directions. In between, it has started moving in the other directions. From where we are getting these directions, I will tell you. Let me erase it. One. Very nice problem this. Concept wise, it is nice. I will tell you. This is known, is not it? Known value. And we want to work on summation fx or x direction only, not fx, x direction only. So this is the x directions. Then we are interested, first case velocity equal to 0. Our expression was something, this was along these directions, known directions, known direction, not value. We have, what we can get that impulse momentum expressions, this. Now initially we don't know anything. V1 x I know, summation fx also I know, dt is unknown when velocity was 0. When velocity was 0. Just a minute. Okay, just a minute. Okay. So here this is known. Initially what we have solved that, let it be V2 equal to 0. If V2 equal to 0, then what will be the corresponding delta t we have calculated, this case. Second case, t is given, dt, here t is given, V2 I don't know. But if I start from the beginning, V2 automatically will give the value. Here it is V2 is positive. Positive means in positive x direction we have considered everything positive. You see, here we have considered negative. Why? It is negative directions. Here this value in x direction component was negative. Why? Because x was positive. This 2p del dt was positive. Why? Because it is in positive directions. So already we are considering the direction. That's why whatever value you told at t equal to 8 second, if it is positive, that indicates it is in positive x directions. If it was negative, then it should indicate negative x direction, means towards down. That's all. It is this, see, whose value we don't know. This value is straightforward. This value also very straightforward, yes, or plus or minus. But this is the things based on the time involved, whether it is 6.46 second or it is t equal to 8 seconds, it is giving the complete picture whether the skip is moving downwards or it is moving upwards. That's why people says this approach is very easy. If somebody, you don't need to go into details, only initial and final configurations if you know, and the variation of the force if you know, then easily you can calculate change in momentum or even whatever the unknown. Here the unknown is velocity. Is it clear now? Hello?
Yes, sir.
Yeah.
Yes, sir.
So yeah, can I move to the problem sheet?
Yes, sir.
Okay. So let's go back to the problem sheet. Dynamics, correct? Okay, this problem sheet, let me check once which number it is. I think 10 or 8. It is 10, yes. Problem sheet 10. Problem sheet 10. Okay. It is told that, first problem, that 20 kg lunar lander, this one, is descending. So acceleration is negative. Onto the moon surface with a velocity of 6 meters per second. When its retro engine is fired, one engine has been fired here, and engine is giving some thrust. Generally what happens, engine is giving thrust, and in thrust direction it's supposed to move, okay, and the engine produces a thrust of t equal to t for 4 seconds, that is varying with time as shown in the figure. Oh, this is a variation of the thrust t in Newton. Okay, this is 2, this is 4, 800. So this slope is 400, is not it? This slope is 400. So it is t second, and it is small time second, it is Newton. Okay. So t, the thrust t for 4 seconds, that varies with the time as shown, and it then cuts off. So at t equal to 4, there is no engine has stopped. Calculate the velocity of the ladder when t equal to 5 seconds, assuming that it has landed. T equal to 5 seconds. So if somebody want to write this is the 5 second. Actually after that it is 0. Up to t, this thrust 0 to 800, then it is becomes 0. So total area basically this, that is the thrust. Okay. Now very interesting to follow this whatever the force has been acting here. Can you tell me force are acting here?
MG.
This problem, mg.
MG.
So mg multiplied by dt or delta t, that is acting downward, correct?
Yes, sir.
Yes, sir.
So if it is y, this is x. Okay, in y directions, mg minus delta t minus t equal to, because this is the mw and this is the t, so this minus t equal to m v2 minus m v1, is not it? What I want to say, in or maybe I'll do the reverse way. This is okay. Do one thing. You make this is x and this is y. Negative direction it is y. Then mg is positive, minus t equal to m v2 minus m v1, where As per the given problem, g acceleration due to gravity is 1/6 of Earth on the moon. So 9.81 by 6 meter per second square. Okay. First
It
one.
is given 1.62 meter per second.
Oh, yes, this is given. So directly we'll use that. Okay. So what we'll write here, m is 200 multiplied by 1.62 multiplied by t equal to 5 second. Delta t is 5 minus, what is this area? Half multiplied by 2 multiplied by 800
Plus 2 into 800.
plus, yes, 2 into 800. Then this is nothing, okay, equal to m, what is m? 200, velocity is v, final velocity v minus 200 multiplied. You calculate, you will get v equal to 2.10 meter per second. Okay, that is done. Next problem. This vertical motion of 3 kg cylinder, m equal to 3 kg, is controlled by force P applied to the end rollers. This is the P of the extensible framework as shown. If the upward velocity v, this is the v basically, upward velocity v of the cylinder is increased from, so v1 was 2 meter per second, v2 was 4 meter per second, delta t was 2 seconds. Calculate the average force RAV under the each of the rollers, each of the, I think it was 2 rollers, okay, TWO, during 2 seconds interval. Analyze the entire system as a unit and neglect the small mass of the framework. Okay. So for this problem, if somebody want to draw this, it is basically,
Sir,
yes,
sir, is the force is transferred from one point to another point, so the velocity is increasing?
no, I'll tell you. So if I draw this way, this type of structure might be you have seen for bridge constructions. Okay, so there will be reaction force like this, R average, here also R average, this is P, this is P, this is 3 multiplied by 9.81 Newton. This is this way, mg. Now you tell me what you are telling, tell me.
Sir, in question it is said na velocity is increasing.
Ah.
So I said that if the force is transformed from one point to another point within the cylinder.
No, it is not force transfer basically. Actually, this mechanism, just like this one, if you pull this one, so what will happen? It will try to have this shape, correct? This shape, or maybe this shape. Is not it? Initially height was this. Then if you put this P and P together, this height will increase. That will give the velocity.
Okay.
It is a little bit complicated geometry. Am I able to tell you that one?
Yes, sir.
It is some complicated geometry, but once you push together this 2P, say it is a toy in your hand, okay, you push together, then due to this mechanism, that height will increase. If this height, say h1, h2, h3, it increase, then that will get the velocity. Velocity will get due to some, how can it get velocity? Velocity will get due to some movement. How it can get that movement with that interval of time? Based on based on the movement of the say this, if you consider just spring like things, it is not spring basically, that way it is getting the velocity. But that will conserve the momentum expressions, that will conserve the energy equations, everything. And if somebody is telling no, sir, this height to this height, that is also true. You want to think this is equations for not instead of momentum equations, somebody wants some other form of expression, then also will get the same. Actually, the ball cannot fly, correct? The ball can move due to the movement of the components. And you are controlling by this P. If P is very, you are applying P very within very small time, then suddenly the length of the system will increase. Then velocity or acceleration will be much more. And if you slowly move this P towards each other, okay, these two rollers, then slowly that your velocity will be more and more, because position of this will be higher and higher. Okay, whatever may be based on the directions. Question is clear or not now?
Yes, sir.
Okay. So now, if somebody want to tell that this is y directions, then we have summation Fy dt equal to m v2 minus or v2y minus v1y. This is the expression, simple. And that is basically 2RAV minus mg 3 multiplied by night 1 multiplied by dt 2 seconds, correct, equal to 3, mass is 3, velocity 4 to initially 2. You can calculate RAV. Okay, 16.22 Newton. Is it okay? Simple. You just put there. Can I move to the next problem?
Yes, sir.
Yes, sir.
Yeah. So this one force P, which is applied to that m equal to 10 kg block, which was initially at rest and varies linearly with time as indicated. P with time linearly it is varying. We can move here. P and T it is linearly varying. If the coefficient of static and kinetic frictions between the block mu s equal to 0.c mu k 0.4 determine the velocity of the block when t equal to 4 seconds. T equal to 4 seconds, velocity you have to calculate. Let's go back here. Okay. We'll write here once again. Actually, this is question number 1. This is supposed to be 2. This is supposed to be 3. This is supposed to be 5. This is supposed to be 4. Okay. Let me write down once again. M equal to 10 kg, mu s equal to 0.6, mu k 0.4. Velocity t equal to 4 seconds. V0 was 0. V1 equal to 0. V2 equal to, you have to calculate, t equal to 4 seconds. Okay. Now, if I want to draw the free body diagram for this problem, it is like this. 10 multiplied by 9.81 Newton. This is unknown Newton, this is friction F, and this is the force P you have applied. P. This is simply FBD. free body diagram, because it is dealing with force only. Okay. Now, what is, say, x, y? Summation Fy equal to 0 will give n minus 10 multiplied by 9.81 equal to 0. N equal to 981 Newton. N value we got. Okay. Now, initially it is in rest. Now P is 0. Starting P equal to 0. So this is basically 25 slope, 104. This is
Hello,
P.
sir.
Yes, yes.
Sir, N value will be 98.1, na?
Okay, 98.1. Yes, yes. Thank you. Okay. So this is slope will be 25, 10 by 100 by 4, 25. Now how much time it is required to start motion? We have to calculate. If T1 is the time required to have the motions, T1 time is required to initiate motion. Then from the summation fx equal to 0 for the T1, or simply if I want to write that P minus F equal to 0, or P equal to F. What is F? F will be F limit static. So F limit static equal to mu S multiplied by N, 0.6 multiplied by 98.1 Newton. And if somebody calculate 58.9 Newton. So what is P? P is 25 T1 equal to 58.9 Newton. Okay. Actually this 25 unit is Newton per second. This unit is Newton per second, Newton per second. Okay. So it will be cancelled out. So T1 somebody can calculate 2.355 second. So 2.355 second may be here. 2.355 second. At that time, it will start with motions. Before that, it was at rest. Now, in motion conditions, summation FTD equal to m delta v. What is summation f for that case? Summation f equal to P minus Fk. Is not it? Kinetics. P is 25T. What is Fk? Fk equal to 0.4 multiplied by 98.1 Newton. That is 39.2 Newton. Okay. So minus 39.2. (25T minus 39.2). That is delta F. Now we can write that 25T minus 39.2 delta F dt equal to m. M is given 10 multiplied by v minus 0. What is initial velocity? 0, final velocity is v. What is the indications? What is the limit of the integration?
Upper limit 4, lower limit 2.355.
2.3, whatever value, 335 or
yes,
something.
Sir.
Okay. Then you can get v equal to 6.61 meter per second. That's all. So what we did, initially it was at rest. So I have to draw the free body diagram completely, correctly. So considering it is in static conditions, and time required to initiate motion is T1. So up to the limiting case, if I want to draw the free body diagram, it says summation Fy equal to 0, that is n minus mg equal to 0, n equal to mg equal to 98.1 Newton per second. And F limit for static mu s n 58.9. F limit for the kinetics, that is mu kn, that is 30 how much 39.2. Now what is the time required t to initiate the motions? For that one, summation fx equal to 0 will give p minus f equal to 0 or p equal to f limit static, or 25 t1 equal to 58.9, t1 equal to 2.355, whatever you will get, you will write that second. Now after that, it will be in motions. So once motion will start, there will be some accelerations. Why? Due to unbalanced force delta summation f. This unbalanced force will give accelerations, but we don't need to calculate the accelerations. We are using impulse momentum expressions. And if we utilize this, summation f dt equal to m delta v. That means 25t minus 39.2 dt limit t1 to 4, t1 is 2.355 equal to m v minus m multiplied by 0. Velocity initially was 0, so velocity we can calculate. That's all. Any doubt up to this?
No, sir.
Okay, another two problems we have. Okay, space is one issue. Maybe we can utilize that space. Okay, now a tennis player here, a tennis player strikes the tennis ball with a racket while ball is still rising. So different color. So this is the path. Ball is still rising. Here v1. Okay. The ball speed before impact with the racket is 15 meter per second, and after that speed is this. It is given 10 degree and 20 degree. Okay. If I draw this, I need some space. Let it be here. Let it have horizontal directions. Okay. And this is positive x. This is positive n y. So initially 10 degree, v1 equal to 15 meter per second, and v2, okay, angle I should do little, 10 degree should reflect there properly. Just wait. Okay. This is 10 degree. So v1 15 meter per second, and it is 20 degree. v2 22 meter per second. Achha. And mass is 60 gram. This mass is 60 gram. G, here G stands for gram only. Okay. In contact, if the 60 gram ball is in contact with the racket for 0.05 second, delta t 0.05 second. Determine the magnitude of the average force R exerted by the racket on the ball. Find also the angle beta made by R with the horizontal. Comment on the treatment of the ball with the weight. It's fine. So input I have already taken. We have to work on that. Okay. Now, so W equal to mg equal to 0.60 by 1000 kg multiplied by 9.81 Newton. So 0.589 Newton. That is the W. Tennis ball weight. Okay. Next is V1. I have written here. V2 is this. and it is racket ball. The ball with the racket. Okay, this is the ball. Now for this ball, you can notice that, let me change the color. This is 2 delta T self weight. Okay. This react basically by the racket will be inclined angle, some angle. Okay, you can see there is some angle. So let's have some component wise, okay, in x and y directions. So let's consider in x directions it is Rx delta T, and in y directions it is Ry delta T. So it is impulse momentum, UILS momentum. Now let's consider along directions. Along x directions, m vx1 plus integration over t1 to t2 summation fx dt equal to m vx2. Okay. Now this v1x equal to minus 15 cosine y equal to 15 sin 10 degree, v2x equal to, it's positive, 22 cosine 20 degree, v2y is 22 sin 20 degree, sorry 20 degree, 22 degree, sorry 20 degree, sorry 20 degree. Now if I use this expression, what is this? 0.06, maybe it is close to 0.0, sorry, not weight, it is mass only. Mass m equal to 60 gram, 60 by 1000, 0.06 kg. Okay, 0.6 m multiplied by minus 15 cosine 10 degree plus this is Rx multiplied by 0.05 time equal to m is 0.06 multiplied by 22 cosine 20 degree. This will give value of Rx equal to 42.5 Newton. What about in y directions? In y directions, in y direction it is m vy 1 plus t1 to t2 summation fy dt equal to m vy2 or 0.6, this is 1, correct, multiplied by 15 sin 10 degree plus positive y Ry delta t minus 0.06, or directly will this w will write 0.589 multiplied by delta t, or maybe delta t, instead of delta t let's directly write 0.05 equal to 0.06 multiplied by 22 V2Y, 2Y sine 20 degree. Okay, then Ry will be getting 0.9 Newton. Now in R 6. Newton. Somebody want to calculate 2 by Ry. Much 0.89 by 6.4 to 9.08%. 9 by 100. Okay, that means in this problem, in this particular problem, Ry is Ry and W, they are comparable. Tennis ball, that's weight is around 9%, more than 9% of the reaction forces. So if you are not considering this W, then there will be 9% error. That's why it is told that somewhere it is told on the treatment of the weight during the. So the consideration of weight of the ball is very much important, because it is at least more than percent of the force of the impulse, or that force in the y directions. Now somebody calculate what is the R value. R equal to square root Rx square plus Ry square. Okay, and beta equal to, with the horizontal, tan inverse Ry by Rx. And this was 43 Newton and this was 8.68. So you have to be careful which directions it is. Ry and Rx. Let's come back here. If this is the Ry, this is the Rx, this angle is 8. That means somebody can write this way. This is the Rx, sorry, Ry. Value wise also you can check. Ry value, how much I told? Just now somewhere 42. 42. No, this is not this.
6.49, sir.
Okay,
6.49.
Ry, correct?
Yes, sir. In the upper case, sir.
Okay. Yes. 6.49 Newton. And this one 42, correct? 42.5 yes, Newton. That means indicates, let it be do little bit concise. This value is very less, like this, 6 and 42. And angle is this basically. Okay. So this angle is the beta. Beta value I told just now 8 degree. Understood? Because this is very close. 8 degree. Beta close to 8 degree means this is very small value, because Ry is much lesser than the Rx value. Any doubt you have for this problem? Should I repeat?
No, sir.
Okay. Now next problem, and that will be the last problem, yes, for the day. Just a few. Okay, just wait. Okay. Sorry, not this one. We are here. Okay. Okay, there is a simple pendulum A, this A of mass ma, mass is ma, of length L, length is L, is suspended from the trolley B. This is the trolley B of mass mg, of mass mg. Just a minute. Okay, trolley, actually this is, expression is saying ma and mb. Actually this is mb, something is wrong, it is mb. Okay, mg will be mb, mass ma and mb. If the system released from rest at theta equal to 0, theta equal to 0, v equal to 0. When this theta equal to 0, v will be 0. Determine the velocity vb at theta equal to 90 degree. This is degree, 90 degree. Okay. Now you look at the system. If system initially theta was 0, velocity was 0. Now we release it. So this A will try to have some rotational, some theta. There will be some theta values. It will, from this horizontal to, it will try to move vertical directions. Once it will do, it will get some angular velocity, and somebody can calculate v equal to wr, omega r. You can get some rectangular velocity also. But as soon as this A is trying to move downward directions, say maybe I can consider maybe like, yes, like this. So this to this direction means this direction. Then that means A is getting some backward directions. Then to adjust this conservation of momentum, this B will try to have some movement in the right directions. So BB will be in these directions. BB will be in these directions. Okay. And maybe if we consider the particular case when theta equal to 90 degree, if I draw this, so one horizontal line like this, roughly I am drawing this. And say this is the A and this is B. So, and it is getting velocity VB like this, and there will be some theta variation like this, or maybe I can write theta dot also, some angular velocity, and this angular velocity will give length multiplied by theta dot, some linear velocity, and A will experience two velocity. One is due to B, that is VB, and one is due to this angular velocity L theta dot. So relative velocity will be VB minus, either VB minus L theta dot or theta dot L theta dot minus VB. But it is expected VB is downward directions, and as a whole the A will move in left directions. A will move in left directions. Now using this idea, as there is no external force, summation fx equal to 0, considering this as the x directions, then delta gx also will be 0. Momentum will be conserved. So somebody can write in that case mb vb minus ma ma say va equal to 0. Why minus? It is in other directions. Or mb vb minus ma va equal to L theta dot minus VB, or L theta dot can be written as equal to 0. Okay, L theta dot will go that side. Okay. Without step jump, let's try here. It is MB VB minus MA L theta dot minus plus MA VB equal to 0, or MA L theta dot equal to MA plus MB multiplied by VB, or L theta dot equal to VB multiplied by MA plus MB by MA. L theta dot, that angular velocity, due to the angular velocity theta dot, we can get linear velocity. Now, if I consider this expression, let's have kinetic energy plus potential energy equal to constant for this system. Then half mv square MAV square plus half MBVB square, that is, or in the left side itself, minus MGL equal to 0, MAGL equal to 0. So when theta equal to 90 degree, it will have MAG multiplied by length, that will be the energy. So this plus this, kinetic energy for A, for B equal to the potential energy. So if I work for that, let me write down here what we got initially. L theta dot equal to VB MA plus MB by MA. Now we got half M B square plus half MB VB square equal to MAG multiplied by L, or half MA this is VA. We got, let me check, VA equal to L theta dot minus VB. L theta dot minus VB whole square plus half MB VB square equal to MAG multiplied by L, or half MA multiplied by L theta dot VB MA plus MB by MA minus VB square plus half MVB square equal to MAG multiplied by L. Somebody can work to get final expression VB equal to MA by MB square root 2GL by 1 plus MA by MB. Once again, what we did, so what we got, once A is starting moving left directions, B will start moving right directions, trolley. So let's have velocity VB and VBA. B is rightward and A is leftward. But in one particular case, a theta equal to 90 degree, we can easily understand, due to this theta, there will be theta dot. If there is theta dot, there will be L theta dot. So there is the relative velocity of A. Okay, one is VB right side due to trolley, and VA is the left side. So effective velocity will be L theta dot minus VB, that we got. Now if we use that, Initially it was 0, finally theta equal to 90 degree. That is the problem given. Then from where we have started here that as there is no force applied, momentum will be conserved. MAVA minus MB minus MAVA equal to 0. Now VA equal to L theta dot minus VB. Okay, and we have worked on that to get relationship between L theta dot. Then if we consider this kinetic energy and potential energy equal to constant, then half MA square MAVA square plus half MBVB square minus MGA is equal to 0. Or you can have some other terms of form also. And if you work on that, finally we will get expression of VB in terms of MA MB GL. So that is VB equal to MA by MB square root 2GL by 1 plus MA by MB. Do you have any doubt up to this?
No, sir.
Okay, fine. So what I can do, I can stop presenting and I can take the attendance quickly. So next day, next Tuesday will be last day as per the theory is concerned. That will be on impact. Okay, on impact. And then revision will be by April 1. Okay, only one day you will get. If you ask any questions, you are facing issues, I will give you the hints for the solution. That's all. We are almost at the end. Okay, now let me take the attendance quickly. Then 25 present, 26, 27, 28, 29, 30. Okay, aerospace all present. Okay, Nitin was absent last day during the exam, the class test. Then CB 77 present, 17 absent, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90. Up to 90, all are present. 91 is absent, 92 absent, 93 absent, 94 present, 95 present. Then CST 58, 59, 59 is absent, 58 is present, 59 absent, 60 absent, then 61 present, 62 present, 63 absent, 64 absent, 65 present, 66 present, 67, 68 present, 69 present, 70 absent. Okay. Then electrical 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59 present. Okay. Now electronics 35, 36, 37, 38, 39, 40 present, 41 absent, 42 present. Okay. 53, IT 53 present, 54, 56, 55, 56, 57, 58 present, up to 58 present. 59 absent, 60 absent, 61, 62 absent, 63, 64 present. Okay, then mechanical 49 absent, 50 absent, 51, 52 absent, 53 present, 54, 55, 56, 57, 58, 59, 60 present. Then 25 25 present, 26, 27, 28, 29 present, 30 absent. Then mining 25 absent, 26 absent, 27 present, 28, 29, 30 present. Just a minute, those who are absent once again, civil 91, then CST 60, CST 64, CST 70, Then IT 59, 60, 61, 62.
Sir, IT 61 present.
61 present. Okay. 62 absent. Then mechanical 49 absent, 50, 51, 52, 53, 53 present. Okay. Then mining 25, 26 absent. Okay. Okay, guys, thank you. So next day will be the last chapter, that is impact, and April 1st will be that just revision. If you have any doubt of any solving any of the problems, we will discuss. Okay. Okay, guys, thank you for your patience. Bye. Yeah.
Thank you, sir.
Yeah. Bye. Bye. Bye.
Thank you, sir.
Thank you.